how many, or yeah, actually, here we don't have to write the number. We just need to know what species are present. And so even though I have two sodiums, but we don't even know what it's going to balance to. So we just write sodium ions and
hydrogen phosphate.
Okay, hydrogen phosphate. Should we break apart this into an H plus and a phosphate? No. This is weak. And
Potassium ions, hydrogen sulfate, and water.
Good. Okay, sodium ions we said before are neutral. What are hydrogen phosphate? Yeah, this is both acid and base. You can look on the acids chart there. The left column's the acid, the right column's the base. It occurs on both sides of that chart. The acids chart, you should, as practice, read through each entry. You know, when a lot of people get a chart like this, they never read all the entries. And so they're unfamiliar with it. And so to become familiar with a chart like that, you should read every single entry. And then questions will come up. They should come up because there's things that don't make sense sometimes. You don't want that to happen right before the test. You know, you want to get those questions cleared up well before the test.
Why is water a major species too?
Because water is a solvent, and the solvent's going to be present in the greatest amount. And so the species we have the most of is water. Now, water is reactive. Do you know what are the chemical properties of water? Well, we'll talk more about it later. But water has acid-base properties. Water actually has redox properties too. Did you know that? Water can be both an oxidizer or reducer. Not a very good one. And water actually can participate in metathesis reactions, but it doesn't really hydrolyze. What happens is it forms hydrates upon precipitation of salts. Okay, so the waters get stuck in the crystal lattice. Or they actually get bonded into there. Potassium ions, neutral. Hydrogen sulfate, acid base. You know, hydrogen sulfate's a much better acid than its base, but we don't care. We're just saying it can either. We're going to figure that out all later. Water is acid base. And so we have three acids. Which one's the best? HSO4 minus. Just look at the chart there. HSO4 minus is right on the border of weak and strong acids. Which one's the strongest base? Actually, it turns out HPO4 2 minus is the strongest base. Just look at the chart. I don't expect you to memorize it. You would just look at the chart. Even on the test, you're going to be given the chart. So you just look it up. And so this is actually very simple because you don't really have to understand anything about structure, composition, properties. You just look it up on the chart, right? Later on, you know, this is the initial phase. The initial phase is just look it up, right? And then just be able to use it. This is not complicated. I think an elementary student probably could do it because you just have to look at a chart like that, right? But, you know, I'm going to require more than what I would require an elementary student, so eventually you have to look at the chart and look for patterns, you know? You see any patterns on the chart? Maybe, maybe not. Yes?
The one on the top is decreasing in base strength, and the one on the bottom to the one on the top is increasing acid strength underneath.
Yeah, I mean that's the pattern, but that's not the pattern I would expect you to, because that pattern is the way the chart is organized. When I'm talking about a pattern, I'm talking about You know, is there something about the 7 strong acids that they all have in common? You know, and other things. And so those are the types of patterns. You know, is there something structurally or compositionally that all strong acids have? You know? Okay, that's the type of stuff. But that type of stuff we'll look at later. Because we're going to be doing. And you already looked at it too, probably in Chem 1A as well. So we pick the strongest acid, HSO4 minus, and the strongest base, HPO4 2 minus, and react those. And so we have to define these because both of these go either way. So the acid loses the proton, or the base, you can think of the base as taking the proton away in the acid. So we end up with sulfate and dihydrogen phosphate. And then we go backwards. All reactions are this kind of competition between the forward and the reverse. So if we were to reverse this reaction, what would the acid, what would the base be? Yeah, and the base is this. This can only be a base. It has no H to give up. This could go either way. But we always define it based on the context of the reaction, not based on the chart there. And so looking at this, which one's a stronger acid, HSO4 minus or H2PO4? HSO4 minus. If the acids follow this, the bases must, is the conjugate relationship. You'll never have strong, weak. You'll always have strong, strong, weak, weak, or weak, weak, strong, strong. If you do get strong, weak, and get them mixed, then something's wrong. So there's reaction here.
Why is HPO4 2 plus a strong, the strong base? Why can't it be a strong acid?
Why is H2PO4 minus a strong base?
No, the one up there, HPO, yeah. Why is it a strong base?
HPO4 2 minus, why is it? It's not a strong base. It's a very weak base, but it's the strongest base out of this list. It's the strongest base out of the list based on the chart there. And so when we go over to the chart, we just look. Actually, I have the chart here. I should have the chart. Did I put it? I forgot to put it in here. I'll show you the chart. So we just look at the chart. Strongest acids per caloric acid on this chart. The weakest acid, do you know what the weakest acid is? You know, usually when you get a chart, you want to know, at least you want to know the extremes, you know? There's a lot of people, what they do is they memorize the extremes. That way, you know, if they're given something that they've never seen before, they can try to place it between the extremes or outside the extremes. And so do you know what the weakest acid on this chart is? Not bicarbonate, not ammonia. It's a weird one. It's this stuff that comes out of there, methane. Methane's not a very good acid, is it? Methane is an awful acid. Is this the weakest acid in the universe? No, it isn't the weakest acid. There are weaker acids, right? Than methane. This is not shown on here. And so, you know, it's a good idea to know some of the extremes here. Hydrogen, we'd never neutralize base with that. It just wouldn't work with any common base. The only time methane's gonna work is if you have a stronger base than what? The only thing that will react with methane is a stronger base than, oh, would methite be strong enough to neutralize methane? No, you'd need a stronger base than methite. And so you can get methane to react with a superbase. You want superbase and superacids. But anyway, let's look at this chart. These patterns that we see, like one of the patterns that's very common in Chem 1A is this: HI, HBr, HCl. Why is HI a stronger acid than HCl? Does everybody know that?
The size.
Yeah, size of the atom bond strength. Why is HF way out of the pattern? Does everybody know that? These are the patterns I'm talking about. These little patterns here that we can learn to correlate with structural information, compositional information, that type of stuff. Not the pattern. This is the general pattern for the chart. The general pattern for the chart is, okay, we have H2. Oh shoot, now I remember. This. Excuse me. Something missing. You know what's missing? Last edit, I realized that H3, we should have H3PO4, we should have H2PO4, we should have HPO4 minus. But unfortunately, those got deleted in the last edit of this chart. So this chart, I need to give it the fixed version of this. Anyway, here's H3PO4, H2PO4, HPO4 minus, HPO4. So HPO4 2 minus is what we're dealing with. HPO4 2 minus is a very weak acid. Very weak acid. But it's still an acid. HSO4 minus and H2O are other acids, so we just look those up on the chart. And so the same thing with this. Initially what you do is you don't overthink it. You don't want to worry about it. You just want to know the method and be able to solve the problem. That's it.
Yeah.
That will get you past, the course, right? If all you know is the method and you don't know anything about the chemistry, you still can make it through and do well, right? But if you want to really get a deeper understanding, then after you master the method, then you start thinking, are there patterns in this, right?
Mm-hmm.
Because if you recognize the patterns, then what that does is this. If an instructor decides to give you something not on the chart, and you know some patterns, you can figure it out. If the instructor, gives you stuff that's on the chart, right, then no problem, right? It's just when they give you stuff not on the chart, can you deal with that? And so that shows two different levels of skill or mastery or whatever you want to call it. And so oftentimes instructors will throw stuff that only people who've looked at this a lot and can recognize things will be able to solve it. And everybody else who just knows how to read it off the chart won't. Then they say, oh, that was nothing like the homework. Yes, that was nothing like the homework. If all you can do is just repeat what's been done. Okay. This is a good question, but don't worry about it yet, and then worry about it later. Can you do the method? If you can do the method, then that's good. Well, let's do this one here next. Why do I say solid sodium amide? Sodium salts are soluble, aren't they? And so, why do I emphasize solid sodium amide? Normally I don't. Like in the potassium sulfide, I didn't, right? I didn't. But this one, I said solid sodium amide is mixed with water. I should say it's carefully mixed with water. What is the formula for sodium amide? you guys know amide?
Yes, amide's a really strong base.
Amide's a really strong base, right? It's one of those ones you should memorize. It's NH2 minus, right?
Yes.
And so Na plus, NH2 minus, sodium amide.
It would steal that proton from water and make it become hydroxide.
Yes. So you know what's going to happen already. You know what's going to happen. This is why it's solid, because sodium amide does not exist in water. Why does it not exist in water? Because amide is too powerful of a base to be stable in water. Even though sodium salts are very soluble, and so this will dissolve in water. But anyway, this is an example. We'll inventory it. Sodium, amide, and water. That's our inventory. Sodium ion's a neutral. Amide is,
Base.
neutral. Amide's a base. Technically, amide could be amphoteric. You know, because if another proton's plucked off amide, we'd form an even more powerful base than amide. We'd form NH with a 2- charge, which would be like a super base. Probably somebody's trying to make it. I don't know who. But, you know, people want to make exotic stuff. Water, acid base. And so the strongest base present is amide, obviously. The strongest acid present is water. And so the reaction is going to be between amide and water. What does it yield?
Ammonia.
Ammonia or ammonia?
NH3.
Ammonia, NH3. We only transfer one proton. It's got to go to 3. Can't go to 4. NH3 and water. Or no, not water. OH minus hydroxide. Hydroxide's good because it's the only it's stable. But when I say stable, hydroxide can be very reactive as well.
That H3 is going to be a gas form this time?
No, NH3 will be aqueous.
Still
It's still in water. There's plenty of water present. Water's a solvent. And so here, this is our base, this is our acid. Going backwards, what's our base, what's our acid? Ammonia is our base. No, ammonia is our acid. Do you see, normally we think of ammonia as a weak base. And in the context of this reaction, it's not a base. It's an acid because we're reacting it with something more powerful, and that would be, well, hydroxide. So now we compare the two bases, amide versus hydroxide. Amide's stronger, hydroxide's weaker, water is stronger, ammonia. Ammonia is a very weak acid, as you'd expect. And so we have driving force here. And so, again, we see the leveling effect of strong base. None of the strong bases, stronger than hydroxide, can exist stable in water. They all react with water to form hydroxide, the strongest base that can exist in water. Now, what I do, let me tell you what I do. I'll throw in other stuff in here. Let's say I did this. This is a trick I do all the time. It screws people up. I'll do sodium amide plus magnesium nitrate.
Uh-oh.
And so automatically people think the reaction should be between sodium amide and magnesium nitrate, which it doesn't happen. Or does it? Actually, this one I might screw people up too much. Yeah, this one I would screw people up too much because we'd get magnesium hydroxide. It would be a multi-step reaction. I would probably try to keep it easier, like calcium. Because, you know, calcium hydroxide is soluble, so it's not going to precipitate. But if I did calcium, and so people are thinking, what's going to form? And so people say, oh, calcium amide's going to form. Calcium amide with sodium nitrate. and then get all confused because they don't know the solubility rules for amide, right? And so, you know, just because there are other reagents, these other reagents might be spectators. You know, I'll throw in some more, like potassium chloride plus, you know. This is why we use this method, the inventory method, because I can throw in 10 reagents in there. You just got to pick the species that are going to react. Doesn't matter how many reagents are in there. The reactants, Good question? Yeah. What is the solubility, what? For amide? Amides are going to be soluble. But the thing is, you know, normally what we do is, you're thinking if you had something like, normally amides are limited because of the way they're formed to alkali metals. And so you aren't really going to see any amide compounds that are going to be like, maybe the alkaline earths like calcium, because of the way they're formed and because they're very reactive. They're usually formed from alkali or maybe calcium. And so you really aren't going to see compounds like iron 3 amide, you know. Iron 3 amide just wouldn't be observed because of how would you get that? You know, how would you make that? It'd be too difficult to make. And so you don't really have to worry about it. And so when you see an amide, it's always going to be paired with a soluble cation. It's the same thing with things like, sometimes the solubility rule is not there, like sodium oxide versus iron oxide. Are the oxide rules on the list? The oxides aren't on the list, but you know, oxides are -2, they're small, and so they got to be comparable to some of the other species you've seen, right? Like sulfides, or what would you expect? Oxides to be more soluble or less soluble than sulfides? Less soluble because of the smaller size, higher charge density, assuming the bonding is 100% ionic. And so things like this, we use other rules. I would say all oxides are insoluble. Like rust, you can't wash away rust, right, with water. So all oxides are insoluble except for group 1 and ammonium. Right? That goes for magnesium oxide and those types of things, unless they undergo reaction. All right, so the first part of this is just to learn the technique. Is it fairly straightforward to figure out? Yeah, it should be. I don't know, but every semester I get, you know, students complain that it's too difficult. But, you know, I think they're just hitting some kind of mental block because if you just follow the rules, you don't have to think. I think they're overthinking it and they're trying to predict things that are much more complex. None. Actually, no, that's a joke. Because it's spread out. It's spread out throughout the book, but it's not like in one place, unfortunately. That's the only reason I made these PowerPoints, because it's spread out. Normally, if it's just in the chapter, I don't. And so, let me tell you, chapter 16, which we're going to get to. Did you cover chapter 16 in Chem 1A? You didn't? You didn't cover structure and okay. Well, that's a chapter that's supposed to be covered in Chem 1A. The start of the acid base, but we don't do the calculations. You go to the end of chapter 16. This is from the end of chapter 16 here. Okay. When I was talking about HCl, HBr, did you guys cover that in Chem 1A? A little bit? Okay, that's in chapter 16. Okay. And so the first part is just to learn the method. The method's not that difficult, so you don't really need a lot of extra. If you get extra stuff, then you're making it too complex, too complicated.
Dr. Chabal, if something's amphoteric, how do you know which is the acid and which is the base?
You don't. You don't?
Because you said that the strongest base was for HPO4 2 minus. Like, how can you determine that?
No, you have to have a partner, a reaction, another reactant to figure it out. So this is your question. Is hydroxide a base?
Depends on what it's reacting.
Depends on what it's reacting with. So if I react hydroxide with amide, is hydroxide the base?
No,
No, hydroxide's the acid. Well, hydroxide's an acid, then that means all hydroxide's an acid all the time?
no.
No, it depends on what you react it with. And so you need to know the other species that's reacting in order to determine if this is an acid or a base. In general, 99.9% of the time, it's a base. And so most people say it's a base, but they're gonna be wrong 0.1% of the time. That's all.
All right. I better understand.
Okay, okay. Hopefully that 0.1% isn't the big point value question on the test, if you only know it as a base, okay? Anyway, this is the next phase. The next phase is this, how can you better understand acid and base strengths in terms? So we have a chart like this. And so a chart like this, the first step is you have a lot of data. In the scientific method, some people ask me, do I need to memorize the chart? Because they want to get an A. They'll do whatever it takes, and they're willing to memorize that chart for me. But I say, no, don't bother memorizing the chart. It's not worth it. And so does that mean they should completely ignore the chart? Well, if I don't have to memorize it, I'm not even going to think about it 1 second. I'm not going to spend any time thinking about it. That's wrong too, right? And so the thing is, when we think about the scientific method, have you ever heard the term data reduction?
Yeah.
Have you ever heard that term? Data reduction. You could Google that too. Data reduction is very important in science. Why? Because, have you looked at Appendix D? Yeah. This chart is a small, actually, I don't know, do I have time? I'll just say it. Basically, if you have, let's say, 300 pages worth of chart like that, that's a lot of chart, right? So that's a lot of observations. And so the first thing the scientists do, they look for patterns, because patterns means you don't have to memorize the whole chart. Patterns means you just memorize the patterns. You memorize the patterns, then you can make predictions, right? Sometimes the patterns are very mathematically concise, so that you can just have a mathematical formula define the pattern. Then we can use that to make predictions. Well, when we think about, acid strength, we should be able to correlate with structure and composition. And so we got a lot of data there, and I look at that and I say, it doesn't look like there's any pattern there, right? And that's because maybe I have to look at it deeper, and I start looking at these things structurally. And so let's look at reactivity and identification of peroxide acids and bases. The reason you want to do this is because not everything occurs on that chart, right? Sometimes you encounter things off the chart, and you want to try to predict what's going to happen. And so if that's the case, then we have to have a deeper understanding of that. And so the easiest is just to look at the chart. But if something's not on the chart, or if you don't have the chart available, then what do? Well, we try to understand things structurally. So we do Lewis structures, right? Lewis structures are based on theory. And so from Lewis structures, we can get an idea of bond strengths, bond polarity, those types of things. This product stability is a little bit out of place. But basically, these are the things, these are the three most important factors that affect acid strength. How strong is the bond? This is right. I is the strongest acid. HI has the weakest bond. This is why HCl is a much weaker acid, because it has a stronger bond. And then when you see oxo acids there, all the oxo acids have the same bond strength because they all have an HO bond. And therefore bond polarity dictates the acid strength. And then some of those, it's product stability. HF. HF is a very, very weak acid compared to HCl because of the product stability. The product stability is it forms something called an ion pair, H plus and F minus. And so those things influence the strength. We can also look at these, this is pencil and paper here. But we could also look at these using quantum mechanics. What's the significance of quantum mechanics? Well, quantum mechanics is the theory that chemists use to understand matter. Right? And so it's the theory of chemistry. And so in quantum mechanics, what we can do is we could look at densities. And so we generate these things. These things are called electrostatic potential maps. The red is negative or positive? The red is negative. I don't know why they did that because, when they did batteries,
Red is always hot.
yeah, the red is the positive terminal. But anyway, it's all right. It's backwards here. And we have these models here, and we can figure these things out. And so we're going to start looking at this more structurally later. So ultimately, we want to see, in these structures, how is the charge distributed? So if I look at acetic acid and compare it to H2SO4, H2SO4 is a much stronger acid, although you can't really tell from here. It's also diprotic acid. Actually, you can tell, because do you see the blue? The blue is positive, and the blue's like hydroxide is going to be attracted to positive, or is it going to be attracted to negative if you're hydroxide? To positive. Which one do you think it's going to be more attracted to? This one. And so this turns out to be the stronger acid. And so this is why we say the strongest acid is going to react, because if you're hydroxide, you're definitely going to be attracted to this, not this. So hydroxide will come and pluck the proton off. Sulfuric acid here. Well, quantum mechanical software is expensive. And so we want to do this on pencil and paper. When we do this on pencil and paper, we try to figure out how the electron density is distributed in the molecule. And so this is something you have to review. So we can do it quantitatively using quantum mechanics. That is calculations and computer. If we want to do it semi-qualitative or semi-quantitative, what we're going to do is on pencil and paper, we're just going to count electrons. How do we count electrons? There are 3 ways to count electrons. We can count electrons via the octet. Octets is the total number of electrons surrounding the atom. We can count the electrons based on formal charge. Formal charge is making an assumption that all bonds are 100% covalent. Formal charge counts the electrons in an atom, assuming the bonds are 100% covalent. So if you have a bond, the atoms share the electrons 50-50. We'll split it down the middle. Oxidation state counts the electrons, assuming that the bonds are 100% ionic. So review octet, formal charge, oxidation state, and bond polarity as a start. This will help you understand acid strength. So Bronsted is not too bad because Bronsted, we always have this chart to fall back on, Lewis acid-base reactions are much more difficult. Lewis acid-base reactions, the goal is to share an electron pair from the base, form a coordinate covalent bond. Have you ever heard of a coordinate covalent bond? A coordinate covalent bond is a bond that results in this way. Both bonding electrons come from a single atom. In a normal covalent bond, let's say you have a hydrogen bonded to a hydrogen, one electron comes from this hydrogen, one electron comes from this hydrogen, we form a bond. Once a coordinate covalent bond is formed, you can't tell the difference between a regular covalent bond and a coordinate covalent bond. It's just in the formation phase that you can see it. This is an example of a Lewis acid-base reaction. A Lewis base is an electron pair donor. A Lewis acid is an electron pair acceptor. BF3 is an excellent Lewis acid. BF3 is an excellent Lewis acid because it's short of an octet. You see, it only has 6 electrons, valence. And so BF3 is highly reactive. And so what happens is ammonia donates electron pair to boron and forms this. You look at the formal charges all screwed up though. Nitrogen is plus, boron has a minus. And so what's better, having 0 formal charges? Do you guys remember formal charges? Or having these formal charges? Well, when we weigh these things out, this is why you need experience. When you weigh these things out, it turns out having the octet's better. This positive formal charge on nitrogen is okay. A positive formal charge on fluorine is not okay. So fluorine will never double bond. And so this is okay. Now how do we identify Lewis acids and bases? Lewis acids and bases are much more difficult to identify. You know, BF3, yes, it should be a Lewis acid because it wants more electrons, right? And so Lewis acids are capable of accepting an electron pair. What's best? Well, having more positive charge density is best. And so you're looking for atoms with positive charge density. Lewis bases are electron pair donors. So for electron pair donors, you're looking for atoms that have negative charge density and a lone pair. And so this is what we do. We do structural analysis. We look for electron-rich areas, you know, high negative charge density, either with oxidation state, formal charge, right, or polarity. And if they have a lone pair, they're going to be bases or base sites. A base site is a specific atom in a molecule that's going to act as the base. Our acids are going to be positive charge density, capable of accepting an electron pair. Capable means that it's either short of an octet or the electrons can rearrange. That is, and I'll show you how that happens. And so what we look for are red regions will be base sites, blue regions will be acid sites. And we look, are those capable of donating or accepting? And so what I see is this is both. This can act either. This can act either. This can act either, but this is not so great probably. But it probably can. Now, is there a chart that ranks Lewis acids and bases? No. And so the strength rankings are much more complex because what we form is a coordinate covalent bond. How would you describe a coordinate, how do you describe a covalent bond? You describe it using MO theory or valence bond theory. Both of those rely on how well the orbitals overlap. And so we have to see how the orbitals overlap. What constitutes good orbital overlap? I'll tell you what constitutes good orbital overlap, having similar size orbitals. So if you have a gigantic sp3 and a tiny s, you don't get great overlap. You know? And so basically it's simple. Usually when we look at the products, we want the orbitals to be somewhat similar. And so the strength rankings are more complex in Bronsted because we have to look at the orbitals. This is called HSAB. HSAB stands for hard, soft acids bases. A hard acid has small orbitals. A soft acid has big orbitals, kind of thing. No, should I say that? Yeah, in a way. Really, it's the base. A hard base, small orbital. A soft base, big orbital. So you can kind of think of it as polarized. Remember polarizability? Yes? No?
Okay.
Yes.
Also, the electron-rich areas, those are acids. Those are acid sites or base sites?
Electron rich?
Yeah.
Okay, always think of this. Acid is positive, H+, right?
Yeah.
And so electron rich would be negative. Those would be base.
Mm-hmm.
All chemistry is electrostatic. You heard that? All chemistry is electrical interactions, so it's all positive and negative. This is why electron maps are so important to chemists. Electron maps are so important to chemists because all chemistry is positive and negative interactions. But it's not just positive and negative. If it were just positive and negative, it'd be so simple. But we also have to look at orbitals. When we look at orbitals, is lead big, soft, or small, hard, lead? Is lead big and soft, or small and hard? Let's compare lead ion to it is bigger and soft, right? Compared to, let's say, iron 3+. Iron 3+ is very small, hard. Does that make sense? What do you think lead would prefer to be bonded to? A soft anion like iodide, which is big, or a small anion like chloride, which is hard?
A bigger one.
A bigger one, soft and soft, gives better overlap. And so lead prefers to be bonded to iodide versus chloride. Probably the difference is not huge, but, right? Soft, soft, right? Silver, iodide, soft, soft. And so hard, soft, acid-base theory is soft likes soft, hard likes hard. Hard, soft don't make a good combination. But we aren't going to get into it because it's beyond the scope of this class. Lewis acid-base reactions we are going to get into for complexes, and that we'll study much more. Complexes are easier because the acid's always kind of the same type of thing. Are we out of time? Well, we have 1 minute. Okay, carbon dioxide, let me just end with this. Carbon dioxide, let's do structural. What are the acid sites? What are the base sites on carbon dioxide, if any? Well, for carbon dioxide, we could do, let's go ahead and just do the charges here really quick. Oxygen, -2, +4, -2. This is the oxidation state. Formal charges, 0, 0, and 0. Bond polarity. Bond polarity, oxygen is delta minus, carbon's delta plus, delta minus. These are the two extremes. You know, this is the charge assuming 100% ionic. This is a charge assuming 100% covalent. The true reality is somewhere between the two. Somewhere between the two is a charge on oxygen between 0 and -2, which we call delta minus, a partial charge, right?
Yeah.
Somewhere between the two is between 0 and +4. We call that delta plus. And somewhere between the two extremes is delta minus here. Now, what are these specific numbers? We could calculate these using quantum mechanics, but we aren't because we don't have the software to do that. And so the base sites are going to be the negative charge with lone pair. And so this is a base site. This is a base site. This would be the acid site if it can accept a lone pair, but it's already got an octet. Can carbon exceed an octet? Not really, but it can. It can if it displaces other electrons. So it doesn't really do it. So if an electron comes in here and pops a set of electrons out, then it can. So we'll see that in here, this reaction. Well, okay, I'll end this now. We're going to finish up this tomorrow.